Hello everyone. The first experiment is about determining focal length of a lens by using Bessel method. Remember our first course about the lenses, light and lenses course. At the course, we told about the lens equation. We can calculate focal length by using distance from the image to the optical center and distance from the object to the optical center. Di is distance from the image to the optical center, and O is the distance from the object to the optical center. And F is focal length of the lens. 1 divided by F will be equal to 1 divided by Di plus 1 divided by DO. After reminding this equation, I want to talk about the Bessel method. Initially, let's look at figure 1. Figure 1 shows us the focal length of a thin lens, and we see two different rays. So incident rays which travel parallel to the principal axis will refract through the lens and converge a point, which is focal point F, and then incident rays which travel through the lens and travel parallel to the principal axis. So you see these two different rays here. So the focal length F of a lens refers to distance between the main plane of the lens and its focal point. So this focal point F can be determined by using the Bessel method, and this method involves measuring the various separations between the optical components of an optical bench. On the right side, the upper figure shows you the optical bench, which is our experimental setup. We will have a screen with a target. We will have a light source in the experiment, and we will have a lens. We will have lens combination. And then we will take some measurements. Which measurements we will take in the following slides, I will tell you. And the formula for the Bessel method is on the right side again. F is equal to A squared minus E squared divided by 4A. So this is the formula for the focal length of a thin lens, and it can be derived by using the Bessel method from the lens equation. So you see here A, and A is on the, please look at the right figure, figure 2. This is schematic of ray paths through the lens. We said that incident rays which travel parallel to the principal axis, it will refract through the lens and converge a point, which is focal point, and incident rays which travel through the lens and travel parallel to the principal axis, and then an incident ray traveling through the exact center of the lens will continue to travel in the same direction after refracting through the lens. So for the convex lenses, you see the pathway of the rays. So here you see A equals B plus G. A is distance between the object G. G is the head of the object, and A is the distance between object and the image B. B is the length of the image, and you see B again, distance between the lens and the image B, and G is distance between the object G and lens. So you see again on the left, 1 divided by F will be equal to 1 divided by B plus 1 divided by G. If you look at this, this is actually our lens equation, remember from our course. And then here, in the place of B, if you insert A minus G, which is equal to actually the distance between the image and the object in our optical center. If you insert this B, if you insert A minus G instead of this B, and then make the cross product here, you will obtain a formula which is actually the quadratic formula, which is G square minus AG plus FA will be equal to 0. Look at the right figure, please. You will see the solution, two different solutions for a quadratic formula. By applying the same procedure to obtain the results for G, you will obtain these G values as in the middle figure actually. And then after that, after obtaining G1 and G2, and then subtracting these two values, we will obtain another formula which is equal to square root of A square minus 4AF. And then at the last stage, the difference A, which is actually equal to the difference of the solution, two different solutions for G. A is the difference between two lens position, which we have on our optical bench. First position of the lens is P1 and the second position of the lens is P2. The difference between two lens positions resulted in a focused image. And then to obtain the focal length, we can rewrite the equation that we obtain by using the Bessel method. F from the equation will be equal to A square minus E square divided by 4A. So if you wonder more detailed, I will tell you obtaining the focal length formula from the lens equation with the Bessel method more detailed, but how we can reach this F by using this quadratic formula. I will solve this in another video, more detailed. You can watch it. So this is our formula for the Bessel method, and the focal length F of a lens refers to the distance between the main plane of the lens and its focal point. We can calculate it by using, we can obtain the this value by using this Bessel method. And then to obtain this, we will measure the various separations between the optical components of our optical bench. So A is equal to G plus B, which is equal to actually the distance between the image and the object. And you see E, which is the distance between our convex lenses. In this experiment, actually, simply we will measure these distances E and A. So also we will determine two positions of a thin lens where a sharp image is formed. We will observe this, and we will determine the focal length of this lens by using the Bessel method. And to see differently formed image on the screen, we will repeat the procedure with various target to screen distances. An optical bench, it is possible to set up a light source, a lens, a screen, and an object to the image in such a way that a well-focused image appears on the screen. Using geometric relationships between the ray paths for a thin lens, it's possible to determine its focal length. So our experiment is about this. Okay, see you at the course.